Alright, so in this video we're going to go through calculating a really simple example of a between subjects t-test. Now, whenever you do an inferential statistical test, it's really helpful to follow a set pattern. And the pattern that I like to follow is based on a textbook by Gravitier and Walnu, where essentially you state the hypothesis, you set the rejection criteria, you calculate the test statistic, then you interpret that test statistic, and then finally you report your results, which is a little addition of my own. So let's go through that. We're going to do it based on this made up data right here, where we have one sample, which corresponds to the numbers 1 through 7, and another sample, which is the numbers 3 through 9. So just real quick, dirty, simple example. Okay. So the first thing that we need to do is state our hypotheses. Now recognize that these are actually the statistical hypotheses, and we always have two of them. The null hypothesis, which states that nothing's going on, everything's random chance, and that in this case, these two samples are coming from the same population, or at least two populations that have an equal mean. So the mean of the population that sample 1 is coming from is equal to the mean of the population that sample 2 is coming from. The alternative, that is mutually exclusive and exhaustive, is that something is going on, and that sample 1 is coming from a population whose mean is not equal to the mean of the population that sample 2 is coming from. So we've got our statistical hypotheses all laid out. The next thing that we need to do then is then set our rejection criteria. Alright, now first thing we need to do is decide upon an alpha level. So what's our decision rule? What probability is going to be so unlikely that if our test statistic has a probability lower of it, then we're going to reject the null hypothesis. So let's use sort of a standard alpha level of 0.05, and let's make sure it's two-tailed. All right. Now, we are going to conduct a t-test, and so our test statistic is going to be on the t-distribution. Now, we know that the t-distribution varies based on degrees of freedom. So we need, before we can actually get a reject or a critical value or anything like that, to know the degrees of freedom for our test. So in this case, the degrees of freedom for an independent samples t-test, which is the same thing as a between subjects t-test, is going to be equal to the size of our first sample plus the size of our second sample minus 2. Now, we can go ahead and calculate this out. We have 7 scores in each, so this would be 7 plus 7 minus 2 to get us 14 minus 2 to get us 12. Okay. Now we would actually go to a table and we would go to, okay, what's our degrees of freedom? And usually the furthest left-hand column. Okay, what's our alpha level? And in how many tails is it? 0.05 and 2 tails to come up with a critical value of 2.179. Now, it helps to sketch out this distribution. It'll become very helpful when we go to try and interpret it. Okay, so here's our t-distribution. Now we know that the t-distribution is symmetrical about a mean of 0. And we know that the extreme values that have a very low probability of occurring are out in the tails. So specifically, our critical regions are all the way out here. Now, let's think about those critical regions. They are the t values that have a very low probability of occurring, specifically less than a 5% chance of occurring, which comes from our alpha level, and the value that bounds them, the critical value, is our t crit right here. So we would have this t crit being 2.179, and this t crit over here would be negative 2.179. Now, when we think about this and what it means when we calculate our test statistic, if the t value that we calculate, our t observed with the OBS subscript, falls inside this critical region, meaning that it is somewhere in this shaded area or somewhere inside this shaded area, that means that that t value has a probability of occurring less than 0.05. In other words, the probability of our test statistic is less than 0.05, and under those conditions, we reject the null hypothesis. So we've set up our rejection criteria. Now the next thing that we need to do is actually go through and calculate out our test statistic. Now, when you do this, it helps to approach it in a systematic way. Now, the way that I like to approach these is based on a problem-solving strategy called least ends means analysis, which basically involves setting up multiple sub-goals to make some way of solving this problem, specifically called an operator, work. Now, how I apply this to this situation is that when I actually go through calculating my test statistic, give me a little more room. First thing I need to do is I start with the overall formula for a t-test. In that case, this t-test that we're using has the mean of sample 1 minus the mean of sample 2 subtracted from the population mean difference divided by our estimated standard error of the estimate. So what I go through and do is, okay, I have this overall formula, and I look and see what I have and what I don't have. I ultimately have this mean difference right here from the population means, because that's based on the null hypothesis, which says they're equal, so I know this will be 0. I don't have either of the mean values yet, but I have the numbers to calculate them. Okay? I don't have the estimated standard error of the difference yet, but I have the numbers to calculate it. So now I go through and I find, okay, let's go successively find the formulas that we would need for each individual part. So, thinking about this, the first formula that I would need would be the mean of sample 1, which would essentially be just adding up all the scores in that sample and then dividing by the number of scores. I would need the mean of sample 2, which would be adding up all the scores in that sample and then dividing by the number of scores. And we can go ahead and do that here real quick, because that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 divided by 7 scores, which would be 28 divided by 7 to get us 4. Here, that would be 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 divided by 7 scores to get us 42 divided by 7, and so that brings us to 6. So now we see that, okay, we have these two values now, but we don't have our denominator, our estimated standard error of the difference. So then you would go and you would look up the formula for this. Now what you would actually find, if you're using the formula sheets that I give you, is that there are two different formulas. One has the variance for sample 1 divided by its sample size plus the variance for sample 2 divided by its sample size, excuse me, that's supposed to be an n, and you would take the square root of that sum. Another one, and I'm just going to add another equal sign versus write this out again, actually calculates it based on pooled variance, where you would have the square root of the pooled variance divided by the number of scores in group 1 plus the pooled variance divided by the number of scores in group 2. Now, you can use this formula if and only if the group sizes are equal. Otherwise, you have to use this one. And seeing as this one will work in either condition, we're going to go about using this formula. So the next thing that we need to find to get our estimated standard error of the difference is our pooled variance. So we need to get pooled variance. We can look up that formula, and that formula will tell us that essentially it's the sum of squares for group 1 plus the sum of squares for group 2 divided by the degrees of freedom for group 1 plus the degrees of freedom for group 2. Now, we don't have any of these values yet, but we do have the numbers to calculate them. So the next thing we would need to do is actually look up the formula for that as well. So the degrees of freedom for group 1, take the simplest one first, is going to be the number of scores in that group minus 1. And the degrees of freedom for group 2 is going to be the number of scores in that group minus 1. Now the sum of squares gets a little more complex, okay, because the sum of squares for group 1 is going to be the sum of all the squared scores in group 1 minus the sum of squares in group 1 squared divided by the sample size in group 1, and the sum of squares in group 2 is going to be equal to the sum of all the squared scores in that group minus the sum of scores squared divided by the sample size. Now, for most of the problems in my class, you won't have to do all this hand calculation, but I'm doing it to be thorough and to show you this system. So now that I've got essentially to the end, I can get all these numbers straight from the raw numbers. I then work my way back up through all the formulas until I get eventually back to this one right here. So now I'm going to go through and I'm going to calculate out these two sum of squares. Now when you do this by hand, it helps so much to add and sum and square these in a table. So if we have sample 1 here, and then there's going to be an x score for there, and we're actually going to need an x squared as well. And then in sample 2, we would need an x score here and an x squared here. Then I would list these out: 1, 2, 3, 4, 5, 6, 7. And then you can go ahead and square these. 1 squared is 1, 2 squared is 4, 9, 16, 25, 36, 49. And then the scores that we have in sample 2 are 3, 4, 5, 6, 7, 8, 9. 3 squared is 9. 4 squared is 16. 5 squared is 25. 36, 49, 64, and 81. Oh, I'm a little bit off the screen. Sorry about that. So then what I would actually do right here is just go ahead and sum them up. Now, I've actually already done this beforehand, so I can tell you that we're at 28, 140, 42, and 280 for the sums. If you add all these up, you get 28. You add all these up, you get 140, 42, 280. So now we can take and plug these numbers back in, and I'm going to work from the bottom to the top. So when we're looking at sample 2, we have for the sum of the squared scores, we have 280 minus the sum of scores, 42, squared, divided by the sample size, 7, which we could get by just going 1, 2, 3, 4, 5, 6, 7. All right, so now we need 42 squared. 42 squared is going to be 1,764 divided by 7 to get us 280 minus 252 to get us, for sum of squares 2, a grand total of 28. Now we would start plugging in numbers here. We need the sum of the squared scores, which would be 140, minus the sum of scores squared, which would be 28 squared, divided by the number of scores in our sample, 7. So 140 minus 28 squared, which comes to 784, divided by the number of scores in our sample, 7. Then, taking it one step at a time, would be 140 minus 112, which is the quotient of 784 divided by 7, to get us a grand total of 28 again. So now we actually have everything we need to figure out pooled variance. So when we think about this, we have sum of squares of group 1, 28. Sum of squares of group 2, 28. DF1, oh, skip these. Hey, what's up? It's finishing up pretty well. I'm recording a video right this second for the module that starts when I am in Minnesota. After that, I can head home if you like. Pizza. I love you. Bye. Sorry about that. All right. So then, I forgot these, so I'd actually calculate these as well. So we would have n, which would be 7 minus 1 to get us 6, and 7 minus 1 again to get us 6, with n being the sample size in both cases. So we would have 6 plus 6. This would get us 56 divided by 12 to get a final of 4.66, repeating, which I'm just going to round off to 4.67 right here. Now we can come back up to right here. So when we think about this, we're going to have 4.67 for the pooled variance divided by the number of scores in sample 1, 7, plus 4.67 divided by the number of scores that we have there, which would also be 7. Then we would take the square root of that sum. This, in turn, because we can just add these because the denominators equal, would get us 9.33 repeating. Divided by 7 to get us 1.33 repeating. Specifically the square root of 1.33 repeating to get us 1.15. All right, so now we have our estimated standard error of the mean. So now we come all the way back to calculating our test stat. Because we now have all the means, we have the estimated standard error of the difference, so we can go substituting in these values. Mean of sample 1 was 4, minus the mean of sample 2, 6. We know this comes to 0, divided by our estimated standard error of the difference, which, looking back, was 1.15. So negative 2 divided by 1.15 gets us a massively huge t-value of negative 1.74. All right, so now comes this next step, right? We have to interpret this test statistic. And I'm actually going to jump back up here and reuse this same space. 1.74, specifically negative 1.74, would be less than 0, but yet still greater than negative 2.179. So we would be somewhere in here. Now, we are not inside this critical region. We are not inside this critical region. We do not fall inside either of the critical regions. So, essentially flipping this on its head, we know that the probability of this test statistic is greater than 0.05. So this is more than a 5% chance of occurring. So in other words, P is greater than 0.05, and in this case, we can't reject. Rather, what we do is we fail to reject. Now, in this instance, we do not have sufficient information to infer that these two samples are coming from different populations. So if this was our results from an experiment, we would say that, hey, look, there is no significant difference here. And speaking of which, let's go ahead and report out what that would look like. So if we were reporting this in APA style, we would say something like, there was not a significant difference between sample 1. This is a good place to report descriptive statistics in the text. So let's go ahead and go the mean of 4 and sample 2. Or mean of 6. Then you would actually need to report each part of this t-test. And APA has very specific prescriptions about this. You need to have a comma to separate it from the rest of the sentence. Then you need to have a t, and this should be in italics, to indicate that you're looking at a t statistic. Now you can't interpret a t statistic without the degrees of freedom, so the next thing you have to include in parentheses is the degrees of freedom, which in this case you're talking about the degrees of freedom for the overall t statistic, which would be 12. And then you say what that t statistic is, which in this case was negative 1.74. Now, this is one space where you have a little wiggle room. Whether you assign sample 1 to M1 or M2 is actually arbitrary. So in most cases, people just report the absolute value of their statistic. So 1.74. It's perfectly acceptable to report the negative if you would like as well. Then we need another comma, and then we make a p-value statement. So we need to let people know what the probability of getting this statistic was. So the probability of this statistic was greater than 0.05. Then we end our sentence with a period. Now you will see in scientific journals where it's actually equal and then some number. That's perfectly acceptable as well. You cannot calculate an exact p-value by hand and not be miserable. So when you're using this critical value method to determine the probability of your test statistic and whether it's greater or less than 0.05, then you just do greater or less than 0.05 and save yourself some time. All right, so good luck and have at it.